My name is John Points, and I'm a consultant analytical scientist based in the United Kingdom. Today, I'd like to give an introduction to the topic of isotopic internal standards. I'll describe what internal standards are in their conventional form and why they are needed, particularly in the case of test methods for trace-level organic molecules, but why conventional internal standards are not enough, especially for test methods that use liquid chromatography with mass spectrometry, LCMS. I will give a basic explanation of what isotopic internal standards are, which inherently makes them more effective than conventional internal standards. Why, in some cases, they are essential, in fact. I have to start by saying, as an ex-analyst, that popular TV dramas have a lot to answer for. The police send their sample to the lab, go for a quick advert break, then come back to receive the answer. This half-eaten cheese sandwich contains 120 parts per billion strychnine. The victim was poisoned. Real customers sending their samples to laboratories now have the same expectation of instant and precise results. The reality, of course, is not quite so simple. For one thing, if you stop to think about the concentrations you are trying to measure, you can appreciate the challenge. To give an analogy, if you imagine dissolving a sugar cube in a village water tank, that is about 100 parts per billion, the sort of levels you are looking at for antibiotic residues in meat. If you dissolve the same sugar cube in an Olympic-sized swimming pool, that would be about 10 parts per billion. And by the time you get down to 1 part per billion, which is the level we are talking about for banned drugs and toxic contaminants, you would have to dissolve it in an oil tanker. But it is not even that easy. Sugar is clearly different to water. In actual fact, what you're looking for may be very similar to everything else that surrounds it. You need to separate the 1 part per billion you are interested in from the 999,999 that you're not. The population of India is about 1 billion. You are looking for one person. So, for the most part, you need extremely convoluted test methods. You may need to extract from your sample, clean it up again using a different technique, concentrate it, and finally measure it. And even after all that cleanup, the measurement technique has to be incredibly selective and sensitive. Most trace organic methods these days use a technique called mass spectrometry, which separates and detects molecules according to their mass. An incredibly selective, but also expensive technique. Either coupled to gas chromatography, called GCMS, or coupled to liquid chromatography, called LCMS. I'll be particularly talking about LCMS. This complexity inevitably leads to a lot of uncertainty in the result. Even in the case of simpler methods, and by dilute and shoot, for example, I mean things like testing pesticides in wine, where you take your sample, dilute it to almost homeopathy levels in solvent, then rely on the selectivity and sensitivity of the LCMS, you may not get the variability of all those method steps, but the trade-off is that you're prone to more interference and matrix effects. Matrix effects are something that I'm going to cover in the next webinar in this series, but it is enough now to say that they make your instrument signal vary in a highly unpredictable manner. So, just to explain what I mean, imagine you're interested in a pesticide residue in a lump of meat. The first thing you may have to do is extract everything into a solvent. So this is just a glorified kitchen blender. You blend each sample with solvent. But this won't be 100% efficient. You'll lose some. And the amount that is lost will vary from sample to sample, tube to tube. Next, you clean up the extract. It could be any one of a number of techniques. This is a picture of solid phase extraction, where you pass the extract through a tube which slows molecules down by different amounts depending on their chemical properties. Again, you will lose an unknown amount, and again, this will vary by sample. Next, you may have to concentrate, and you get the idea: more unknown and variable losses. Then you chromatography, separating molecules by different retention as they pass through another chemical column. And finally, sample-to-sample detector variation, and this can be the most significant factor of all when we're talking about LC-MS matrix effects. Overall, sometimes you can only quote a result with an uncertainty of plus or minus 100% or even greater. Effectively, you know it's there, but you cannot say for certain how much. So what can you do about it? Well, you can add a reference standard to a control sample right at the beginning. This is sometimes called spiking. This means you can measure how much is lost from this control sample. But what you still can't model is the sample-to-sample variation. You have to assume that the losses in your control sample mirror the losses in your actual sample, which is unlikely to be the case, particularly in the case of LC-MS matrix effects, which can vary incredibly from sample to sample. So a refinement is to use what's called an internal standard. This is a reference standard of something that's a similar molecule to the one you're looking for, but which would not otherwise be present in the sample. So, for example, if you were looking for residues of tetracyclines, which are veterinary antibiotics, in meat, you might add a tetracycline that's only ever exclusively used in human medicine. You add the same amount to everything, to your samples, your spikes, blanks, every type of control and calibration standard. So everything that happens to the analyte should also happen to the internal standard. It should mirror every loss and variation. Then, if rather than measuring the absolute size of a detector signal, you measure the ratio of the signal to the internal standard, you should compensate for every variation at every stage, right? Unfortunately, wrong. Well, this would have been a very quick webinar. Although a conventional internal standard is a similar molecule, it is still not the same. It can still behave differently, particularly in an LC-MS detector. Matrix effects are highly specific and vary independently even within one sample. So your analyte signal could be enhanced while the internal standard is suppressed, or vice versa. Using the ratio can actually give more variation than if you had not used an internal standard at all. So what can you do? Well, if you could add the analyte molecule itself as an internal standard, then there would be no problem. By definition, it would behave exactly like the analyte, elute at exactly the same time, and suffer from exactly the same matrix effects. But how do you tell the difference between one molecule that you've added as an internal standard and the identical molecule that you're trying to measure? Well, the answer is to use stable isotopes. Now, to understand what a stable isotope is, you have to think back to your high school model of an atom. It has a nucleus made up of protons and neutrons, which gives the atom its mass. And it has electrons, which have zero mass, but which give it its chemical properties. So this is carbon. It has 6 electrons, which means that it also has 6 protons. And we are taught that it also has 6 neutrons, giving it an atomic mass of 12, number 12 on the periodic table. So far, so good. But although we think of an element as having a certain atomic mass, in actual fact, most of them exist in a number of forms. For example, 1% of carbon is actually mass 13. This just has one more neutron, 7 instead of 6. In terms of chemical properties, it is exactly the same. And unlike carbon 14, which has 8 neutrons, it's perfectly stable. So you can refine it, purify it, and use it to synthesize reference standards. Making a reference standard that is exactly the same as the analyte reference standard, but differs only by mass, and thus can be differentiated in a mass spectrometer, which you remember selects on the basis of mass. In principle, the perfect internal standard. These are called stable isotope standards, or sometimes labeled standards. So here's a hypothetical example. On the left, benzene. On the right, a synthesized analog of benzene, where all the carbon atoms have been replaced with carbon-13. The same chemical, but 6 mass units heavier. Ideal as an internal standard for the analysis of benzene. There are 3 common stable isotopes used to synthesize internal standards for organic reference materials. There's hydrogen-2, usually called deuterium or labeled D, carbon-13, and nitrogen-15. And any or all of them can be incorporated into a reference standard in order to produce an internal standard. So, going back to the original schematic, if the internal standard is a stable isotope, then you can be confident that it will exactly mirror the analyte through each individual stage of the method. And critically, you can be confident that it will suffer from exactly the same LCMS matrix effects as the analyte. So this time, when you measure the ratio, you know that you've compensated for every potential source of variation and uncertainty. Right? Yes. Well, usually. There are some important technical considerations in both the selection and use of stable isotope standards, and I will cover these in the next webinar. If you do not account for these, you can still go wrong. But generally, stable isotope internal standards give a massive reduction in measurement uncertainty. Now the effect can be seen from this figure. It's quite complex, but these are real results. A sample of blood serum containing just over 2 parts per billion of testosterone was accurately prepared, and this is shown by the red line on the chart. Then it was repeatedly tested by LCMS using 6 different calibration methods. The dot shows the average result for each. The error bar is the spread of individual replicates. So sets 1 and 4 were using a stable isotope internal standard. Set 1 was with matrix matching, which means standards were prepared in blood serum extract. And set 4 was without, so in this case standards were prepared in solvent. You can see that they both gave the right result and had a very tight spread of results. Sets 2 and 5 were using a conventional internal standard, which was nandrolone in this case. You can see the spread of results is all over the place, and even with matrix matching, which is set number 2, results range up to 3 times the true value. But the most concerning set is probably number 6. This was using straight calibration against reference standards in a solvent with no internal standard. And if you did not know the true value, which you usually don't, you would think you had a really tight and accurate set of results. There'd be no clue that your answer was actually wrong. Just like to finish on one final, quite important point. A stable isotope internal standard only works because it's uniquely matched to the analyte. So if you have multiple analytes, you also need multiple internal standards, or one for each analyte that needs to be accurately quantified at least. In the previous example, there would have been little point in using your testosterone D3 to also ratio a whole suite of hormones other than testosterone. So, to conclude, isotopic internal standards are invaluable to achieving accurate quantification in the analysis of trace organic molecules. But in the case of LCMS, I would change invaluable to essential. Thank you.